Section 4.5, again, optimization problems. There are two methods to solve the problems in this section. Take a review. The first method is called the closed interval method. To find the absolute maximum and minimum values of a continuous function on a closed interval, 3 steps. Step 1, find all the interior critical points. Interior critical points means the points inside the interval. Say this curve has 3 interior critical points. This one, tangent line horizontal, tangent line horizontal, and tangent line horizontal. So for this curve, find these 3 points. Then compute function values at the critical points and also at the 2 endpoints. Compute function values at these 3 points, also at the 2 endpoints, because a maximum or a minimum can appear at endpoints. Okay. Then step 3, make conclusion. The largest of these function values is the absolute maximum value of the function over this closed interval. The smallest function value in step B is the absolute minimum value of the function over this interval. Second method is called the open interval method. Over an interval, low guarantee, the function has an absolute maximum or an absolute minimum. Over a closed interval, it is guaranteed by extreme value theorem. To find maximum or minimum over an open interval, also 3 steps. Find all the critical points inside the interval, because maximum or minimum can only appear at a critical point. So find all the critical points. This curve has 3 critical points. Then step 2, sketch the graph of the function. Sketch the graph of the function. So from the sketch, we can see whether or not the function has a maximum or a minimum. And also we can see the location of the maximum or the minimum. Then based on the sketch, we can make conclusion. Say for this curve, we can see that this curve has low maximum over this open interval AB, because this one is open down. But it has a global minimum. The minimum, the location is this critical point. Why for the closed interval, why we don't need to sketch the graph of the function? Because when a curve is on a closed interval, it must have maximum, have minimum. We don't need to sketch its graph to see whether or not the function has maximum or minimum. Yeah. I want to show you 2 more examples today. In the first example, we need to use the closed interval method, and we use the open interval method in the second example. Example 1. A piece of wire of length 60 is cut, and the resulting 2 pieces are formed to make a circle and a square. Now the question is, where should the wire be cut to maximize and minimize the combined area of the circle and the square? Here is a diagram. This is the wire. We cut the wire somewhere, and I use X to denote the length of this piece. Then the other piece is 60 minus X. Suppose I use this piece to form a circle and the other piece to form a rectangle. This circle, the circumference is X. By the circumference formula for a circle, then we have 2 pi times the radius is X, the circumference. Now from this equation, we have this circle, its radius is X over 2 pi. The perimeter of this square is 60 minus X. So one side of this square is 60 minus X divided by 4. Okay, now with this information, we can tell the combined area. What we need to find is minimize and maximize the combined area. I let A denote the combined area. It is area of the circle plus area of the square. Area of a circle is pi r square, but r now is X over 2 pi, so area of this circle is this term. Area of the square is one side square, okay? So it is a 60 minus X over 4 square. Now I simplify this sum to get this. This is the combined area of the circle and the square. X cannot be negative because X here, it is the length of one piece. It cannot be negative. X cannot be greater than 60 because the length of the whole wire is just 60. So X cannot be the greater than 60. So the value of X is between 0 and 60. The question is how to choose X between 0 and 60 so that A is minimized or A is maximized. This is the question. Because this interval is a closed interval, so I apply the closed interval method to solve this problem. Step 1, find critical points inside the interval. So I compute derivative, take derivative on A with respect to X. Okay, then 4 pi constant, move it out. 1 over 16 constant, move it out. Derivative on x squared is 2x. Derivative on 60 minus x squared, I use chain rule to compute it. So 60 minus x is u. So u squared derivative is 2 times u. 2 times u. And then times derivative on u. Chain rule. So 60 minus x derivative is -1. So we get this result. This is derivative of A with respect to x. Okay. Now to find critical points, I set derivative to 0 and solve this equation. Then I get critical point is 26.39. Step 1. Step 2. Compute function values at the critical point and also at the two endpoints. Function is here. This is the function. Yeah, function is here. Right. Now plug in 26.39 in x here, then we get function value at the point is this number. And also compute function value at left end point 0. Plug in 0 in x, then I get function value is this number. Function value at the right end point is this number. Now, step 3, make conclusion. Among these 3 numbers, the largest is this one. So the combined area reaches the largest when x is 60. What it means? When we use the whole wire to form a circle, then the combined area is the largest. The combined area reaches its minimum when x is this number. That means that when we cut the wire at this number, then the combined area is the smallest. Example 2. Find a point on the parabola that is the closest to the given point 1, 4. The graph of this equation is this parabola. The graph of an equation is the set of all the points that satisfy the equation. Now the question is, on the parabola, which point is the closest to this given point? I arbitrarily pick a point on the parabola and set its coordinates x, y. Then the distance between this point and this point is this by the distance formula. Distance formula. Now the question is how to find x, how to find y, so that distance d is minimized. From the given, we have x is y squared over 2. I plug in this equation in x, then I get this. So x, the variable, is gone from the d equation. So d only depends on y. Pay attention. Here, y is independent variable. Y is not a function. D is a function of y. D depends on y, but y is independent variable. The range for y is from negative infinity to positive infinity. That means that y can assume any number, yeah, from negative infinity to positive infinity. Okay, now the question is how to choose y so that d is the smallest. Because this interval is an open interval, so we apply the open interval method to solve this problem. In open interval method, we need to compute derivative on this function for critical points. This function is quite complicated. It has a square root. When you compute it, the derivative difficult. So instead of minimize d, we minimize d square. D square has low square root. Why we can do that? The rationale behind is d and d square, they reach minimum at the same y, at the same point y. So we can work on d square and determine why there d square is the smallest. Okay, now I let f of y below this function. So in the following, I want to minimize f by the open interval method. Step 1 of the open interval method, we need to find critical points of the function f in this interval. So compute derivative, take derivative on the function f with respect to the independent variable y. The first term, derivative, I can use chain rule, to get this. And also I use the chain rule to compute derivative on the second term. Then I get this. 1/2 times y squared minus 1. Take derivative with respect to y. Then I get this. And similarly, y minus 4. Derivative with respect to y, it is 1 minus 0. Now, simplify this expression, then we get this. Okay. Now for critical points, set derivative to 0 and solve the equation for y. Then we get 1 critical point. It is 2. Second step of the open interval method, roughly sketch the graph of the function f. Just roughly. We just need increasing, decreasing. We don't need concave up, concave down. Okay, now draw an xy plane and put the critical point 2 here. Okay, now from negative infinity to 2 over this interval, I arbitrarily pick a point, say pick 0. Plugging 0 in the derivative, then I get negative a negative number. So over the interval, negative infinity to 2, everywhere derivative less than 0. Therefore, the graph of f is decreasing on this interval. Similarly, on the interval 2 to positive infinity, arbitrarily pick a point, plug in the point in derivative, then we see that derivative positive. That means that on this interval, everywhere, derivative positive. And therefore, on this interval, the graph of f is increasing. This is a rough sketch of the graph of f. From this sketch, we can see that at 2, at the critical point 2, f has a global minimum. So, make conclusion. When y is 2, the corresponding x, we can get x from this equation. So when y is 2, x is 2, this point is on the parabola. This point has the smallest distance from the given point. The distance is square root of 5. The point 2, 2 from the given point, the distance is square root of 5 from this equation. Plug in 2, then distance is square root of 5.